Okay. So we've already talked a little bit about energy, right? We said with any chemical or physical change that happens, there is a energy change that goes with it. We talked about exothermic and endothermic reactions, right? Does an exothermic reaction release or absorb heat? Exothermic reactions release heat, right? I think this is the same exact slide from last week. So burning something is exothermic. It feels hot. An instant cold pack absorbs heat. It feels cold. That's endothermic. Burning balloon of hydrogen, exothermic. This is another change. Physical change, chemical change. This is the hydrolysis of water we talked about, I think maybe the first week. This one's actually chemical because it's not just evaporation. We're actually taking water and breaking it into hydrogen and oxygen. So it is no longer the same thing. Yes, it went from liquid to gases, but they're different gases. It's not water gas. But here, energy is being used. Do you think this is absorbing or releasing energy?
Absorbing.
What makes you say absorbing? You're right. You're right.
We say it needs the electricity to break apart the bonds, so we have to take it in.
Right, right. So you can look at this two ways. You can look at the chemical way, and you can look at it the your logic way, right? They hooked electricity up to it. Clearly it must need energy, right? But you need the energy to break the bonds to separate the hydrogen and the oxygen. Okay. So kinetic energy is the energy of motion. How many people have taken physics at some level? So you've probably dealt with kinetic energy, right? So the kinetic energy exists at all levels. So when I throw this across the room, when it moves, it's going to have kinetic energy. The same exact principles work on the molecular and the atomic scale. The atoms flying around have kinetic energy. Temperature is a measure of the kinetic energy of the molecules or atoms in your sample. Something with a high temperature means that this thing moves. A high temperature means that the atoms or molecules in your sample are moving around fast. A low temperature means they're moving around slow. There's also potential energy. Potential energy is a little more nebulous of an idea. In terms of motion, potential energy is energy that something has because of where it is. So, if I have this marker, and I hold it here, and I drop it, it starts moving, right? When it starts moving, it's gaining kinetic energy. But we can't randomly make energy. That kinetic energy has to come from somewhere. When I hold it here, it has potential energy. It's potential because if I let go of it, it will fall. Okay? So at this point, there's potential energy, and when I drop it, all that potential energy gets converted to kinetic energy. Potential gets converted into kinetic. This marker here has less potential energy than the marker here. Because you know when I drop something, the longer it drops, the faster it moves, right? And the faster it's moving, the more kinetic energy it has. So that kinetic energy had to come from the potential energy. Potential energy can also be considered in the form of chemical energy. And this is, don't try to wrap your head around this. Basically, it means if you have two things that can react, there's potential that if they react, they can release energy in an exothermic reaction. It's not as visual as a marker being held up. So this is a ball, okay? So it works the same if I just hold the marker and I throw it out, okay? So if I hold it here, it has potential energy because it's off the ground, right? But if I throw it up, I'm putting kinetic energy into it. That kinetic energy is not coming from gravity pulling it down. I am putting kinetic energy into it. But if you watch it, when it gets to the peak, it kind of slows and it just kind of hangs there, right? So as it goes up, instead of the gravity turning potential energy into kinetic energy, it's actually taking the kinetic energy that I put into it and turning it into potential energy. So once it gets to the top, it basically stops, and at that point, it's all potential energy. So if I just let it fall, now it has more kinetic energy when it hits the ground than it would if I dropped it from down. So potential energy and kinetic energy just get transferred back and forth between each other. So, looking at this artist's rendition of molecules flying around, making assumptions about how fast molecules are moving based on the little speed lines, which actual molecules do not have, which one do you think has the higher kinetic energy? Why A?
Tail's longer.
Right. The little speed dust coming off the back, the comet trails or whatever it is, makes it look like A molecules are moving faster. If they're moving faster, they have to have more kinetic energy. We measure energy with several different units. Okay? Heat is energy that gets transferred between two things because they have different temperatures. So if I have a hot object and I put it into cold water, what direction do you think the heat is being transferred?
Into the water.
Into the water. Heat goes from hot to cold. Okay? Every day you really think about heat in one way or another. It's really going to help you if you think of heat as a tangible thing. I mean, we talk about it's hot outside, there's a lot of heat out there. But heat is energy, like light. It is something you can measure. It's something you can move. An air conditioner moves heat out of your house. It takes the heat that's inside and puts it outside. You can move heat. In chemistry, we measure heat in either joules or calories. In some cases you will use joules, in other cases we'll use calories. And these are generic units for energy. You can use joules and calories for any type of energy, but we're just going to be working with heat. 1 calorie is 4.184 joules. And I believe that conversion, yes. This conversion is going to be very important to you, but it's on here. But these calories are not these calories. These calories have a capital C. Calorie with a capital C is a kilocalorie or 1,000 calories with a lowercase c. Blame nutritionists, not chemists. Okay? They took our word and they made it their own by putting a capital on it and thought that made sense. Okay? If you look at nutrition labels from other countries, Europe or Latin America, a lot of them will say kilocalories. They make sense. American nutritionists don't make sense. Okay? You have to look at whether something has a capital C or a lowercase c, because it makes a huge, huge difference. So, how many calories with a lowercase c are in one serving of whatever this is?
190,000.
190,000. So, That's a lot more energy than 190, right? 100, right.
800,000 joules.
That's why they do
Yeah,
it.
yeah, so
Turn you off. Turn it all the time.
It's like a game show where everything, all the points are in hundreds, right? Why do they need to be in hundreds? You don't need the zeros. It just looks better, right?
It's ridiculous.
I don't know.
800,000 joules per serving sounds really bad.
So can you compare like food to like electricity in the sense of like how much electricity would take?
You can exactly, yes.
You saying I can eat electricity?
No. So this says it has organic whole grain wheat, organic evaporated cane juice, and natural flavor. What do you think it is? I honestly don't.
It's Rice Krispies.
Is it Rice Krispies?
Frosted Flakes.
Rice Krispies cannot be organic.
Whole grain. It's
Well, what I don't get is, I'll be honest, I'm not an organic person.
corn.
What I don't get is,
Seeds,
if you're gonna eat organic whole grain wheat and organic cane juice, are you okay with natural flavor?
Probably.
Probably not.
I'm really not that picky.
Well, then it's,
I don't know.
you're reading the ingredients list.
That makes sense.
Maybe Cocoa Puffs, maybe. Like whole grain Cocoa Puffs.
That wouldn't make sense.
I don't know.
Probably like a protein bar or something.
Well, there, it's a mountain cereal.
It's a cereal,
Yeah.
This is
It's
It's
some
probably
sort of
some
cereal.
basic cereal that no one wants to eat.
fruit.
Some
Cheerios.
whole wheat.
I was gonna say
grain.
Cheerios.
Oh, it could be, yeah, Raisin Bran
Or
maybe.
like the honey nut Cheerios.
Raisin Bran.
It would say raisins.
Yeah.
Well, maybe it doesn't have raisins.
Maybe it's like
It's a
Wheaties or
brand.
something.
Or the Wheaties, yeah.
I don't know.
Maybe it's generic.
Moving on, moving on.
So it's just nice.
So remember, capital C is 1,000 calories with a little c, which is the same thing as a kilocalorie. Make sure you look at that C. Is it a big C or a little c? So, how much energy in joules is in a serving of this? How would you do that?
You multiply that by 190,000
190,000 times 4.184. Yes. So let's do it using dimensional analysis. We have 190 calories, right? And 1 calorie equals 1,000 calories.
That makes sense.
You should have just done Mortal Kombat, spell it with K.
And then 1 calorie equals 4.184 joules. And we abbreviate joules with just a capital J.
Well, so for us to not be confused with the capital C and lowercase c,
Mhm.
can you just do instead of the 1 big calorie, like the big C, can you just do the 1
So you-
kcal?
If you wanted to make the conscious decision to change it right here,
Yeah.
you could. If you caught that it was a capital C and you want to just get rid of that source of potential error, you could do that, fix it then and there, and not have to worry about it. It's up to you. Do that math, is a whole lot of joules. A joule is a very small amount of energy. Okay? Does anybody know where this 4.184 came from? It's kind of a weird number.
Kilowatts.
21 gigawatts.
So, what they did is they figured out how much energy it takes to raise the temperature of 1 gram of water 1 degree. So if you have 1 gram of water, which is 1 milliliter of water, and you raise the temperature 1 degree, Kelvin or Celsius, doesn't matter, but not Fahrenheit, it takes 4.184 joules. So that's something somebody measured. So then they defined that as 1 calorie. So if you had 2 grams of water and you wanted to raise it 2 degrees, how many calories would you need?
Say that again?
2 grams of water,
Okay.
2 degrees.
4.
4. Exactly.
I just guessed the next number.
Wait a minute.
It's not too good for it.
Okay.
The 2
So we're going to take this information, what we just talked about in terms of heat, and get specific. Okay? This is specific heat. And this is a specific idea. Specific heat is its own thing. When you add heat to something, the temperature is not always going to change the same amount if you have 2 different samples. So if you add 1 calorie to 1 gram of water, it's going to raise the temperature 1 degree. But if you add 1 calorie to 1 gram of a metal, it's probably going to go up by more than 1 degree. What determines how large that temperature change is called the specific heat. And every material has its own specific heat. So this is the amount of heat required to increase the temperature of 1 gram 1 degree. So what is the specific heat of water?
1 calorie.
1. Yeah. This is the specific heat. How much heat you need to raise the temperature of 1 gram 1 degree. The units are joules per gram degree Celsius or calories per gram degree Celsius. Okay. Pretty much every case, you're going to have a table of specific heats, or the specific heat's going to be given to you, and so it's automatically going to have the unit on. Okay. But if you think about it, it makes sense. If we just look at joules per gram, right? We said it's how much heat per gram of sample, right? Joules per gram. And it's also how much heat per degrees Celsius that you want to change it. So if we ignore the gram, it's joules per degree Celsius. But both the mass and the temperature matter. So it's just joules per gram degree Celsius. So if you can think about it mathematically like that, these units make complete sense. So we said specific heat of water is 1 calorie per gram degree Celsius. It's also 4.184 joules per gram degree Celsius. Same thing. So this is what a specific heat table looks like. They really vary. If we look through, there's aluminum, that's a metal, that's a very high specific heat, right? There's gold, that's really low, 0.129 versus almost 0.9. Water is 2 as ice. Liquid water is really high, right? Water, I think liquid water is the highest thing on here, right? This actually makes life on Earth possible. Why do you think that is? The fact that water has a high specific heat.
So it doesn't adapt.
The way it keeps moving.
You're really close.
So it does.
What would happen if it had a low specific heat?
The water cycle.
It would die.
There would be no water.
There would be huge temperature fluctuations, right? We're almost all water.
Global warming.
Global warming would have a larger effect, yes. If we're all water, if we absorb a bunch of heat, our temperature actually doesn't change all that much because water has a very high specific heat. But if we were made out of metal and it got hot out and we absorbed a bunch of heat, our temperature would change a lot.
You'd be sweating like a lot more for no reason.
Where if you're metal,
Metal
you wouldn't
don't
sweat.
sweat.
But you're on the right track.
Yeah.
You're on the right track.
You should have that.
Okay. So, here's an equation for you. This equation is not on the cheat sheet. Okay? I don't know why it's there, but I don't control the cheat sheet. You will see this multiple times, including on the quiz next week and on the final exam. Okay? you need to know this equation. So this is heat equals the mass of your sample times the specific heat times the change of temperature. And when we put these into symbols, we get these little triangles. Anybody know what these triangles are?
Change.
They're delta, which is change. So this is delta H, is change in heat, equals mass times specific heat, which is C. Specific heat is capital C times temperature change, delta T. Some people like to use a Q instead of delta H. It is the same exact thing. A lowercase q is the same thing as delta H. So that would be Q equals MC delta T. Whereas we have delta H equals MC delta T. To me, delta H is more descriptive. It's change in heat. Where they got a lowercase q from, I don't know. So,
Where they get the C from?
there's only so many letters they gotta keep reusing
It's
them.
like not even in the ballpark.
I don't know. So here's an example of a specific heat question. So this is how much heat do we have to add to 15 grams of water to raise its temperature from 25 Celsius to 75 Celsius. So what's my equation? Fast, right?
It'd be 50 equals 50 degrees Celsius. Right?
So, right, so it's asked, which of these variables is the question asking for? What are we trying to find?
The change in heat.
Change in heat. We're looking for delta H,
Oh, yeah.
right? So, we need M, C, and delta T from the question.
So
They have to be in there. So what is my M?
15.
15.0.
15.0 grams.
15.
What is my C?
Use calories, it's one.
1. And or 4.184.
So, okay, so we'll make it easy, we'll take 1. It's not specifically given to us, but it says it's water. And water is the one specific heat you may actually know off the top of your head by the end of the class, okay? So we're gonna say specific heat is 1 calorie per gram degree Celsius. What is my delta T?
50 degrees Celsius.
50 degrees, okay?
Point out.
It's going to make a difference which direction the temperature goes.
This is going to be negative.
So, think about this. If the temperature change was negative, is my energy change going to be positive or negative? Negative. So the temperature change, the sign on the temperature change is going to determine the sign on our heat. Because we can't have negative mass, and we can't have negative specific heat.
Well, the colder something is, doesn't it lose more energy?
Right. So, if we're heating something, the temperature is going up. Are we adding heat or taking heat out? We're adding heat, right? That's hopefully pretty clear to see. So, our delta H should go up. It should be positive. So, just keep that in mind. So, when we do this math, we're going to get a positive number. Think to yourself, should I have gotten a positive number? And yes, we should have. Because temperature is going up, we must have added heat. So we get 15 times 50, 750, and we have 360. $750 point calories. That's how much heat you would have to put in. Okay? Here's another one. Take a look at that.
Same thing, but it cools. So it's
Same thing,
negative.
right.
Negatives.
It's the same problem. 15 grams of water going from 75 to 25. So the only difference is that delta T is negative 50 degrees Celsius So we get negative 750 calories. Make sense?
The G and C just cancel out.
In terms of units?
Yeah.
Yeah, because here we have G and C on the bottom, right? Here G is on top, there degree C is on top. So those two cancel those two, and you're just left with calories. So here they did it in joules. You get the same thing. It's just 4.184 instead of 1. Broke my cap when I dropped my markers. So this is a thinking problem, okay? Nobody ever likes thinking problems. Think about it.
C.
If you can answer this question, you understand specific heat. So, if you're any good at taking tests, you can probably figure out it's either going to be that one or that one. It's not going to be the one in the middle, one of the two in the middle, because that just wouldn't make sense. So, we're going to eliminate A and C. So, it's asking which one has the highest specific heat.
D.
Why D?
Well, okay, you said if it has a greater specific heat, that means, like water, for example, it's not gonna change as much
Right.
as.
Oh, the whole block is wax.
Yes, so
Not
it's-
the white stuff.
no. All
Okay,
of the
yeah.
yellow is wax. The white is how far through it melted into the wax.
Oh, okay.
I was like, this is proportionately fucked. The white stuff is the wax.
No.
No, that makes sense.
Yeah, D.
But yeah, no, because it didn't change as much when it was heated, meaning it has a high specific heat. Or the
Because
greater
the-
specific.
The heat was divided by a larger number because of its greater specific heat, so it had less energy overall.
That's what I'm getting at.
So you will say D, right? Does anybody say
Well,
B?
Yeah.
I think it may be B because if they're all heated to the same temperature, that means they were eventually at that temperature. So when they cooled down, it took them longer to reach.
Oh, same temperature, yeah, it would be
Ground
round because it would lose energy.
Yes.
It would be B.
Oh.
So let's look at our equation. We have
Oh, wait.
delta H equals MC delta T, right? They're all the same mass. So M is going to be the same for all of them. So we can ignore it. Delta T, they start at the same temperature, they end at the same temperature, right? So we can ignore delta T. So how large our change in heat is directly determined by our specific heat. Now, what's going to melt more wax? Something that releases more heat or less heat? More heat, right? The more heat you put into the wax out of your block, because it comes out of your block into the wax, the more wax you're going to melt. So, is the highest specific heat or the lowest specific heat going to give you the highest delta H, meaning you melted further? Right. It's the larger your C, the higher your delta H. The higher your delta H, the more you melt. So, which one has the highest specific heat? B. That's what it's a thinking problem. You gotta think about it.
Let's do another one.
Which one has the lowest specific heat?
C. C. Finally.
There's not many options to go, other options for that question.
What confused me about that one is that they actually appear to be different masses.
Yeah, that's.
They're different sizes.
For volumes of these different.
Because they're different metals, so they're going to have different densities. So to get the same amount of mass, you're going to have different values. So in every situation, the overall change in heat is going to be 0. So going back, any heat that got released by the block got absorbed by the wax. And it was the same exact amount, okay? No heat got lost anywhere. So when we talk about a chemical reaction, we talk about the system and the surroundings. The system is our reaction, and the surroundings are everything else. If I have a beaker with the reaction going on in it, the beaker itself is surroundings. The bench under the beaker is surroundings. The air around that beaker is surroundings. The planet, Pluto, is surroundings. Do they still, they don't teach you Pluto is a
Dwarf
planet?
planet.
Dwarf planet, okay.
It's not a real planet.
It's a planet. Okay.
I was gonna talk about this.
So, if delta H is positive, that means that the delta H for our system, I'm going to back up and rephrase this. If delta H for our system, our reaction, is positive, that means it gained heat. It took in heat from the surroundings. We said that was endothermic, right? That is heat being absorbed into the system by our surroundings. The opposite is exothermic, where delta H is negative. That's heat going out from the system into the surroundings. Here's another question. This time we have aluminum. Specific heat is given to us. The question is, how much heat is transferred? And what is the sign of Q, or the sign of delta H? And what does that mean in terms of its significance? So what's my equation?
Delta H equals.
156 grams.
Delta H equals what? What's the rest of the
negative
equation?
36 goes.
Just letters.
Oh,
Letters.
M
Oh.
times
M times
C times delta T.
delta T. Okay. Which one are we solving for?
Delta H.
Delta H, right?
So we put 156.
So our mass is 156 grams. Our C is what? 0.895 joules per gram degree Celsius. What is my delta T?
Negative.
49.5.
Negative 50.
It's not exactly negative
It's
50.
75 minus.
49.
Yeah,
Oh,
it's
sorry,
45.5. So it's negative 49.5
So our answer is going to be negative.
degrees Celsius. So our answer is going to be negative. When you do this, what do you get?
Negative 6,06911.
Is it joules or calories? How do we know?
Joules.
Why is it joules?
That's the only one that doesn't cancel.
Right. The specific heat they gave us had joules in it.
But it also doesn't cancel. It's the only one that doesn't cancel.
Right. Right. If the specific heat they gave us had calories, not joules, our answer would have been in calories. So we need 3 sig figs. So I'm going to turn that into a 0.
Can't even tell.
You can't tell.
Their exact numbers, the specific heat.
Specific heats, yes, but everything else has 3 sig figs. Right. So, yeah, specific heat you can treat as an exact number. So, what is the sign of Q?
Negative.
It's negative. So, is it exothermic or endothermic? Exothermic. Negative delta H or negative Q is exothermic. Answer. Here's another type of specific heat question. Think about it. do you think? We'll probably eliminate copper, right, in the middle. So is it the highest specific heat, aluminum, or the lower specific heat, lead?
Lead.
So aluminum.
Well, let's look at our equation. They're all 50 grams, right? So M is the same. Delta H is the same, right? So if we just rewrite this, delta, and get rid of our M, C delta T, and delta H has to stay the same. As C goes up, what direction does delta T go? Down. They have to go in opposite directions. So what's going to have the largest delta T? The highest C or the lowest C?
So the aluminum.
Lowest. We just said they go in opposite directions.
Can we like not use the letters for a second?
So if you have a high delta T, you're going to have a low C. A high C would give you a low delta T. That's math way of looking at it, okay? You can think of specific heat as like the cost, okay? How much energy does it cost to make the temperature go up? So if you have 1 kilojoule of heat that you can spend, and these are the prices on the things, which one is going to give you the largest temperature change for your money?
Lead.
The lowest one, right? The thing that costs the least, you get the most of it with your money. You can think of it the other way also. When you're cooling it, so this is where heating it. How much money do you have to put into it? When you cool it, it's like selling it again. The thing with the highest specific heat is worth the most. So you get more energy out of it when you sell it. This one, you're not going to get as much out of it, okay? High specific heat means large energy changes for small temperature changes. Low specific heat means low energy changes give you large temperature changes, okay? Does this make sense? Okay. You can think of it money-wise. Whoever grades your final exam is not going to know that you thought of it in terms of money, unless you cross out grams and write dollars. So this is our same nutrition fact. Proteins, fats, and carbohydrates have very distinct nutrition values. All proteins have 4 kilocalories, which is our calories with a capital C, 4 calories per gram. All fats have 9, carbohydrates have 4. It doesn't matter what the source is. Proteins, fats, and carbohydrates are very set in stone nutrition values. Okay, does that make sense? In one equation, if you know how to work it, you're fine. But you have to remember that one. Okay, so we're going to move on to gases. Okay? So in the slide packet, the slides that were in the video were not in the packet. Lindy pointed that out to me. I just posted them on Canvas. They're right next to it in a separate file. Okay, if you want those. So we're going to pick up where the video left off. Okay? Here we have 2 more drawings. Which one has the highest pressure, assuming they're at the same temperature?
B.
Why B?
There's no molecules.
Exactly. There are more molecules. Think of pressure as the molecules hitting the side. Okay, say this is the inside of a balloon, this is the inside, that's the wall of the balloon. You can hit the wall with more force either by hitting it harder, meaning the molecules are moving faster, or just hit it more often. And so this one has more molecules, so it's going to hit the wall more often. So the pressure is higher. How would, thinking of this conceptually, how would raising the temperature increase the pressure?
It increases energy between the particles.
Right. Increasing temperature does what to kinetic energy? It raises it. So all of a sudden these molecules are moving faster, so they're going to hit the wall harder, which pushes that balloon out, makes it expand. So here is a random metal can, looks like from the 40s or something, and they hooked a vacuum up to it. Why did it crush when they hooked the vacuum up to it? It removed the molecules from inside. Why does that make it crush?
There's
The
negative
pressure on the
Sucking the
outside,
pressure.
that's it.
Right. So, here, before you apply the vacuum, what is keeping that can from being crushed by the atmosphere?
It's not the same.
The
Well,
atmosphere?
The part of the atmosphere that's in the can, right? The air that's in the can is hitting the inside of the walls outward and with the same amount of force as the atmosphere outside is hitting the wall inward. So it's just getting constantly hit like this. It's not going anywhere. As soon as you suck the air out from the inside, all of a sudden you have the air molecules on the outside hitting it, but there's nothing hitting back out. So the air molecules hitting it crush it. So it can be tempting to think of this as a suction that sucks the walls in, but it's actually a force on the outside that pushes it.
So if you did that in a vacuum, it would still crush.
That's catchy. So you're saying if you put the can in a vacuum and then hooked another vacuum up to it?
Yeah, and pulled the contents out of it, it would still crush.
No, because there would be nothing on the outside to crush it.
So if you had a strong enough suction, you could not crush that can.
No, because there's absolutely nothing on the outside pushing in.
I don't believe that.
Well,
You don't have.
I mean, you can't make a perfect vacuum. There's no way to do it. If all of a sudden there was, this universe would cease to exist.
If you're floating around in space, hypothetically,
We're moving on.
and you stuck the air in a water bottle, it won't crush.
You and I can debate this during break.
What happens when you go inside a black hole?
I think we're outside a black hole. The more interesting question is what's in the black hole.
Boom.
Okay, we can measure pressure using different units again, okay? And unfortunately, there are going to be a number of units here. Maybe the one you're most common with are PSI. Does anybody scuba dive? No scuba divers. Does anybody use gas tanks at work?
Yeah,
Whether-
the tire pressure in my car.
True, that's PSI also. There you go. Yes, so we're used to PSI, okay? In terms of a tire, your tires are probably somewhere between 30 and 35, would be my guess. At least you're supposed to be, would be my guess. So, this is sort of our everyday unit. We don't use PSI in science, because pounds.
Yeah.
We don't use pounds in science. Okay. So when you read about atmospheric pressure, you check the weather and it tells you the barometric pressure. Does anybody know what units they give it to? It's inches of mercury. which sounds really, really weird, right? What do inches of mercury have to do with pressure? This is how they used to measure atmospheric pressure. They had a dish full of mercury, and they had a little tube upside down in it. So the bottom end is open here. So if you imagine, the harder you push down on this liquid mercury, you're going to force more liquid up into the tube. So the stronger the atmospheric pressure, the more you're pushing on the mercury, the more it gets forced up. So they would actually just measure how many inches up the tube the mercury went, and that was the inches of mercury.
So we can't use pounds, but we can use inches?
We're not going, no, because we're not going to use inches of mercury. We're going to use millimeters of mercury. So here's inches of mercury. We use millimeters of mercury a lot in this class, okay? A millimeter of mercury is the same exact thing as a torr, okay? You're probably more likely to write torr. Questions are more likely to say torr than millimeters of mercury, but they are the same exact thing. We'll use torr and we'll use ATMs, and ATMs are atmospheres. So one atmosphere is defined as the normal average atmospheric pressure, and that happens to be 760 millimeters of mercury, which is also 760 torr. We won't use pascals in here, but pascals are another unit of pressure that scientists like to use. I think that conversion is on here. Yes, it says one atmosphere equals 760 torr, and in parentheses it says millimeters of mercury. So you don't need to memorize this, although we're going to use it so many times you probably will. So here's a conversion. This one has pascals, but we're given the conversion between pascals to atmosphere. We need to get from pascals to atmospheres and then to torr. So I'm going to use dimensional analysis. What's the number I'm starting with?
8.25 times 10 to the 4.
Pascals. What's my unit?
Yeah.
Has to be pascals. Where am I trying to get to?
18.
Right, I need atmospheres and torr. Which one's the first one I'm going to go to? Well, we only have one conversion factor that has pascals in it.
Oh, so you're
Right.
in the atmosphere.
Right, so I have to go to atmospheres first, which is the first answer it asks for, and then I can go to torr. Right. So it says 101.325 pascals is 1 atmosphere. So what is that number divided by that number? Eight 814.211?
Yes.
Okay. So we've got 3 sig figs, so 814 atmospheres. Now I can just take this one more step and say 1 atmosphere equals 760 torr, so it's 814 times 760.
619, 000.
619,
3 0.
how many zeros?
3 zeros.
3 zeros. So we found converted pascals into atmospheres, and then atmospheres into torr. You may see atmospheres with capital letters Don't let that throw you off. It's the same exact thing. Different people write it different ways. Something's not right.
Because the six fit in science, yeah, it's just a tour in scientific communication.
Right, but
But why do you multiply this times
Yeah,
60 towards
that's not the same as that. That's 0.814 atmosphere. Somebody do this again.
8.25 times 10 to the fourth divided by 101,325 is 0.81.
Yeah. 0.814.
That's 616.
That's 618. So there are a number of things that we're going to look at that affect our gases. Okay? One of them is going to be pressure. What other things can you think of that affect gases? Heat, temperature,
Density?
density,
Area of surroundings?
say that again?
The area of the surroundings?
Yeah, what do you mean?
Like a balloon. If you had this much air outside the balloon, you just cram it into this balloon.
So volume.
Sure.
There.
Volume affects gases. Okay? Those are the three big ones, and the fourth one is how much gas you have. Okay? So we got volume. We're going to measure volume in liters. We have pressure. For the most part, we're going to use atmospheres. Temperature is going to be in kelvins. Okay? Specific heat, we use degrees Celsius. Here we use kelvins. No other choice. If it involves gases, kelvins. Mathematically, Celsius will not work. Okay? Mathematically, we can use milliliters. And we'll see situations like that, where it's whatever volume you put in, the answer has the same volume. For temperature, you cannot put in degrees Celsius and get out degrees Celsius. It's going to completely mess you up. Kelvins. Then we also have number of particles, which we're going to measure in moles. Okay, so we talk about gases being ideal. Okay? And by ideal gas, we mean that they have very linear relationships. And all of these equations that we're going to talk about require these linear relationships. If you double temperature, your volume doubles. Okay? In real life, it's not exactly perfect. But our equations assume an ideal gas that does behave perfectly. So, let's first look at the relationship between volume and pressure. If you release a weather balloon, why does it eventually pop? Why doesn't it just float up to the planet Pluto? What about the pressure?
So that's because from so little outside pressure.
Right.
it pushes it.
Exactly. As you go up in the atmosphere, the pressure decreases, right? All of a sudden, the molecules on the inside of the balloon are still hitting just as hard as they were originally, but there's not as much pushing in, so that the balloon expands and expands and expands and expands until eventually the balloon pops, right? If you have a bubble at the bottom of the ocean, and it comes up through the ocean, what's going to happen to the size of that bubble?
Good.
Why is it going to increase? Our balloon got bigger as it went up, right?
I don't know if it's going
Warm
No, it wasn't.
The PSI.
What about the PSI?
It,
There's less water pressure outside.
Right.
Right. Right.
So I should go ahead and-
So just like in the atmosphere, where there's higher pressure down at ground level and up, the deeper you go in the water, the higher the water pressure. You get all that water above you pushing down. So as the bubble rises, there's less and less pressure on the outside of the bubble, and it expands. So if you were to very generically describe the relationship between volume and pressure, how would you describe it?
Volume increases,
It's the opposite.
pressure decreases.
They go in opposite directions. As pressure goes up, volume goes down. As pressure goes down, volume goes up. And we can look at it from the opposite direction. So here we were saying, what happens if we change the pressure? What changes, what happens to our volume? If you take a cylinder, okay, with gas in it, and you compress it, what's going to happen to the pressure inside the can? It goes up. That's something you're familiar with, right? You're decreasing the volume, so pressure goes up. They go in opposite directions. If you take that can and you somehow expand it, what happens to the pressure inside? It goes down, right? If you work with a syringe at any time, you may be familiar with it. If you take a syringe and you cap the one end and you try to pull the plunger out, what happens?
It doesn't.
It won't go out.
Good, unfortunately.
What if you cap it and you try to push it in? As you push in, it gets harder and harder and harder to push, right? As you push in, the pressure on the inside is getting higher and higher until you can't push it anymore. So this is the graph showing the relationship between volume and atmospheres. Don't worry too much about it. It's just showing exactly what we talked about. As volume goes up, pressure goes down. As pressure goes up, volume goes down. Okay? It's directly opposite of each other. That's all you have to remember. So here is our pistons, just like our syringe. Okay? Which one has the higher pressure? B. You have the same amount of gas in both. This one has a smaller volume, so it has to have the higher pressure. Let's look at this graph. Okay? This one is graphed a little bit differently, so we actually see a linear relationship. Okay? So let's pick a point. Let's pick,
200.
you're gonna pick one that doesn't have a
100.
Okay, 100.
100. Okay? What is the temperature when we double the volume?
I'm gonna go with 5. Double the volume?
Okay,
That
so
means it
here,
goes to 2.
we're here, we have 1 liter of volume.
So now we need 2. So now, it goes
So now we
500.
need 2.
So yeah, it does.
500
But why did
versus-
it go from 100 to 500? We said it should be linear. If you double one, you should double the other.
So,
Because it's not linear.
But it is linear. Graphs don't lie.
wait a minute.
What's going on?
Zero started
That's because Celsius is fucking us.
Exactly.
Oh, true.
373 times 2
Exactly.
is 773. It has to be in Kelvin. Don't put that on the final exam.
There's a write-in, I'm doing it.
If you're going to put that on an exam, put it on something I'm grading.
What do you teach?
It's your words, I'm really saying.
I did not say that. I have video. I have video proof. I did not say it.
I think it's like it's facing the screen at the time.
Okay. So here's our first equation. Okay. This is on the cheat sheet. Okay. You don't have to memorize this. This is called Boyle's law. We said pressure and volume go in opposite directions, right? In math terms, that's how you write that. That's saying pressure is proportional to the inverse of the volume, which means they go in opposite directions, proportionately. If you double the pressure, you halve the volume. If you halve the pressure, you double the volume, okay?
So that symbol is inverse.
Yeah, no, 1 over V is inverse. That's proportional to.
I've never seen that symbol.
Now you have now.
Do that on the back of ours.
You're going to see that in some of the next coming up slides too. So, mathematically, if we get P and V on the same side, we get PV is proportional to 1, which means it's constant, okay? So, long story short, you derive this equation. P1 V1 equals P2 V2. This equation applies to situations where we're changing something. We're either changing the pressure or we're changing the volume. The ones apply to the pressure and the volume before the change. Twos apply to pressure and volume after the change. There are 4 variables here. Your problem has to give you 3 of the 4. You cannot do it if you only have 2 of the 4. So then it's just an algebra problem. Plug in the 3 variables that you're given and solve for the 4th. And they can give you any 3. They can give you these 3, they can give you these 3, they can give you those 2 and that 1. It's the same difficulty problem. Plug the 3 in, solve for the 4th. I took that problem and rearranged it for you. On cheat sheet, they just give you the P1, they give you that. So you need to be able to do the rearranging yourself. So here's an example of using Boyle's law. So we have a sample of gas. That sample is 2 liters. We decrease the pressure from 1.2 atmospheres to 0.2 atmospheres, keeping temperature the same, and ask what is the new volume. So first of all, which variable are we trying to solve for? V2, the second volume. So the other 3 have to be there. What is P1?
2.20. Or no, that's mine.
The original pressure is 1.2 atmospheres. What is V1? 2.0 liters. What is P2? 0.25 atmospheres. So we have P1 V1 equals P2 V2. All we have to do is plug them in. 1.2 times 2.0 equals 0.25 times V2. And you solve for V2. When you do that, you can, it's not up there. V2 equals 9.6 what? We put in liters, we got out liters. Mathematically, if this was 2.0 milliliters, it's going to be 9.6 milliliters. But you get out what you put in. Volume, that's okay. Pressure, that's actually okay. Whatever pressure you put in is the pressure you get out. Temperature is the one that has to be Kelvin. Here's another one. The only tricky part about these questions is figuring out what the question is asking you for. After that, it's just plug and play, right? So, which variable is this asking us to find? It's one of the P's, right? What pressure is needed? We're given two values, right? what is, let's start with the volume. What is V1?
1.5 milliliters.
V1 is 2.50 milliliters. We're going to compress it
Okay.
to,
That's atmospheres.
sorry, thank you,
450.
455. We're going to compress it to 282 milliliters, right? So it says, what pressure is needed to compress 455 milliliters of oxygen gas at 2.5 atmospheres to a volume of 282 milliliters? Is 2.5 atmospheres P1 or P2?
V1.
It's about 50-50, right? So, there are two ways to look at this. There's the test-taking way. In terms of words, it says 455 milliliters of oxygen gas at 2.5. The 2.5 is linked to the 455 in terms of words. And 455 was V1, so P1 must be 2.5. Okay, so that is correct. The other way to look at it, it says we need to compress that at 2.5 to a volume of 282. Okay, yes?
Why does it, the question says, what pressure is needed to compress for 455? Like, it's almost like saying, what pressure goes with 455?
It's saying if you have 455 milliliters, and those 455 milliliters are at 2.5 atmospheres, what pressure do you have to apply to that sample? Extra pressure do you have to apply to get it to shrink to 282? Okay. So now we just plug it in and solve for P2. So we have 2.50 atmospheres times 455 equals P2 times 282 milliliters. And what do we get? 4.033 atmosphere. How many sig figs do we need? 3. So we've got 4.03 atmospheres. These problems are really easy for you to do a double check. Okay. If you need to do the Aaron Rodgers double check when you're sitting there, go ahead. Okay. But you can think about this. Should the pressure have gone up or gone down to make the volume smaller? It should have gone up. Did it go up?
Yes.
Yes, it did. If it went down, you know your math is wrong. You don't know that you're right, but you know you have it in the right direction. So odds are you have it right. So, why?
Atmospheric pressure is lower.
Yes, exactly. You have the same amount of gas molecules inside, it's pushing out. Why does it have to be lightly salted? It doesn't.
Yeah, it could be.
It doesn't have to be. It'd be the same exact thing. It's just a picture said lightly salted, so I threw lightly salted in the pot. Be glad I'm not a professor that does this crap on tests, because they do exist. Okay?
I think they'll literally ask why are they lightly salted.
They'll throw in all kinds of unneeded information, so you have to sort out what's needed and what's unneeded. So if you are not 100% confident in what you're doing, you're in trouble.
Flight 729 flying at 637 miles per hour northeast by 375 mils.
Exactly. So what's the relationship between temperature and volume? This is something you deal with all the time, right? It's starting to get colder outside. What are your tire pressures doing?
Lowering.
They're going down, right? So that's the relationship between temperature and pressure, right? In the winter, when it got, in the spring, when it got hotter, imagine you had a really old crappy tire and it wasn't strong and it was able to expand and contract with the volume, okay? What would happen to that tire when it got hot?
Probably bust.
What would happen before it broke?
Would it expand?
It would expand, right? So as temperature goes up, what happens to volume?
It goes up.
It goes up. As temperature goes down, what happens to volume?
Goes down.
It goes down. So the relationship between temperature and volume is they go in the same direction. Proportionally, again. If you double the temperature, you're going to double the volume. Again, we have our nice little linear graph showing us proportional. V, volume, is proportional. T, temperature. Do our math magic, and we get Charles' law. Okay? Charles' law is V1 over T1 equals V2 over T2. This one is in here also. It's given in a slightly different format. This one is V1 over V2 equals T1 over T2. But if you can do algebra, it doesn't matter which one you start with. Plug the 3 in, solve for the last one. Remember, has to be in Kelvin. If it's not in Kelvin, you're in trouble. I didn't say. So again, I've rearranged it for you, but in only one format in the cheat sheet. You need to be able to do the algebra yourself. Here's an example of Charles' law. If carbon monoxide gas, when it's 25 degrees Celsius, 25 degrees Celsius is more or less room temperature. We're going to cool it, assuming pressure stays constant. We're just changing one thing at a time at the moment, until it's 100 milliliters. What is the new temperature in degrees Celsius? Okay. So our equation was V1 over T1 equals V2 over T2. Which variable are we trying to find? T2, the final temperature. So that means we have to have V1, T1, and V2. What is my V1?
150 milliliters.
150.0 milliliters. What is T1? 25.0 degrees Celsius. What is my V2?
100 milliliters.
100.0 milliliters. Plug them in and go, right? No.
You have to convert Kelvin first.
Convert to Kelvin. So, you remember how to convert from
No.
Celsius to Kelvin?
Minus 273.15.
You're gonna add. It's add 273.15.
Celsius to Kelvin.
Yes,
Kelvin.
So it's 273. It's 298.15. Correct?
Sure.
Right?
He says it.
Yes.
Yes. Did you have a question?
No,
No? You sure? If you got it, ask it.
Well, can you just do it by just plugging in the numbers and then figuring out the math instead of doing all that? Or you have to go through everything to get the answer that you have, like,
What's the everything?
like how you put D1, like you did, you said D1 over T1, so that would be 25, right?
But it has to be in Kelvin.
Okay, so yeah, okay.
Yeah.
So you
You
can't
have
change
to
it
convert it before you plug it in.
Okay, yeah.
Is that what you're asking?
Yeah.
Okay. If you're, I don't know, if you were asking, do you have to list these on the side? You don't. You can put them straight
Oh, no,
into the
no.
equation. But,
I messed up, I didn't convert the, oh, you were right.
okay. So now we have Kelvin. So now we can plug it in. So we have 150.0 divided by 298.15 equals 100.0 divided by T2. And T2 equals what? This.
It doesn't matter if we use milliliters or liters, right?
Correct. But you get out whatever you put in. So we're putting in milliliters. As long as they're both milliliters, we're okay. We can't have milliliters and liters. You may run across a problem where one of them is given to you in milliliters, one is given in liters. It doesn't matter which one you use, but you have to convert one of them to the other unit. It doesn't matter which one. What does this come out to be?
Negative 74.4.
Negative 74.
Whoa, it can't be negative.
It's
There's-
50.31.
Right, just the Kelvin?
Oh, in
$198.76.
Celsius, 198.
Oh, okay, you took it all the way to the end. I was like, there's no negatives here, we can't have negative. Okay, so what is the Kelvin?
198.76.
That's Celsius.
Point, no.
The Kelvin is the 74.4, negative 74.4.
198 is Kelvin.
You can't,
198.
It's 198.
198 Kelvin. 198 Kelvin, okay. Stop, breathe. We plugged these numbers in. We got, solve for T2, we got 198. Our temperature was in Kelvin, so we got out Kelvin. Does that make sense?
Yeah.
But our question asked us, what is the new temperature in degrees Celsius? So now we have to take the Kelvin that we got out of our equation. Yes.
How did we get the 198?
Is that T2 not 198?
No, I have the slide. I'm getting 50.312.
Is the slide wrong?
No. Because don't you divide the 150 by 298 and then multiply that by 100? Correct?
So we're going to multiply it over. We got
Are you cross multiplying?
150 times
Oh.
T2 divided by
That's not-
298.15 equals
It's been a long
100.
time.
Does it come out right? Is it 198?
Yeah, it's 198.
198? Are you getting that?
Oh, yes, 199.
Yeah, 199.
So, okay. The way I like to do algebra, I like to condense it as much as I can. Okay? What is 150 divided by 298.15? Just this right here.
0.5031.
So I have 0.503 equals 100 divided by T2. So then 0.503 T2 equals 100. T2 equals 100 divided by 0.503, which is 198.
You're right.
The way to go.
You got it? Okay. So we got out 198 Kelvin. That's what our equation spit out for us. How do we go from Kelvin to Celsius? We subtract 273.15, which comes out to be negative, what was it? Negative
74.3.
Negative 74.4.
negative 74.4 degrees Celsius. Okay. Now, do your discount double check. It doesn't make sense. It says it's cool. It says right in the question it's cool, right? So hopefully our temperature now is lower than it was, which it is. We went from 25 to negative 74. Let's take our break. We'll start at 35 after on the clock.
Your fans in space.
What?
Can they be crushed? From
It
internal
makes
pressure.
sense though, because you need the pressure to press on the outside. Just because it's a vacuum,
You need negative pressure on the inside.
The negative pressure is the absence of pressure.
Yes.
It's like cold air that isn't cold, not hot. Something has to push
But
it.
you can have negative pressure.
But it appears to be negative pressure. There is not an actual suction force. It appears to be to our eyes, actually pushing from the outside, getting away.
Saying you cannot make a can crush from the inside in the vacuum. I don't believe that. It'd be like you can
the
jump out
suction
of
itself
a big
is not
ISS
pressure.
with a water bottle. You suck the air, it would still crush.
Because it's not a perfect vacuum. The space is not a perfect vacuum. You cannot have a perfect vacuum.
I don't believe that either.
I mean, think, if you go out, okay, say you have a can that had gas in it, right? And you go out of the International Space Station and you open it up, what's going to happen to that gas? It's going to go out. All of a sudden, it's not in space. Space isn't a vacuum, it's a perfect vacuum. There's a gas. Right?
That's like so minimal.
It's minimal, yes. So, you know, real world situation where it's not perfect vacuum. If you were to somehow get a better vacuum inside, yes, it would. But if you had a perfect vacuum outside, you could not crush it by sucking it out. If you had a perfect vacuum on the outside, it would go a lot from the inside out.
But it could withstand the pressure, 1% of pressure in perfect vacuum. I feel like you could crush it from the inside. If you had it strong enough, like, I don't know, maybe a little bilge pump. I feel like you could suck enough gas out.
There has to be something to push from the outside, if there's nothing to push from the outside.
If we disagree,
Numbers are the same. Are we looking for if we can find, and like what they have, and see if we can get that much stuff? Like, that's what we need, and just multiply with this to get what we need. Like, don't that, I guess, like, I don't know, we have them, that we're the manufacturer that has these items, or they have them, we need it from them?
You are the manufacturer. Or you can say, I'm the manufacturer, can I make these tool sets?
Oh, okay, I thought you were like the guy that's gonna buy what you need for
No,
something.
basically, I was asking, if there are 2 players per tool set, and you have 1,000 players, can you make 600 tool sets?
Oh, okay. I thought you were, okay, I see.
And
I
then-
thought you were a buyer, and this is how much you said, and this is how much you need. That's what I thought.
Well, the thing is, say you're the manufacturer, I'm the buyer. Okay? I call you up, I say, I need 600 tool sets. You go into your warehouse, you figure out you have 1,000 players, 2,000 screwdrivers, 3,000 wrenches. But every tool set has to have these many each. And you figure out, do I have enough to make the 600 tool sets?
Yeah, you do. No, you don't. You still don't have enough anyway.
You have 3,600 wrenches. You have 3,600 wrenches. Right? No, you need 3,600 wrenches.
Be like 3,000.
Right. So immediately, it's no.
Okay, so either way, that's not an
No
answer.
matter how many screwdrivers or pliers you have, you don't have enough wrenches.
Oh, okay. Sorry about that.
No, it's okay. So, any Brooklyn Nine-Nine fans?
Yeah.
As I was going through this lecture, I realized we have Boyle's Law, we have Charles' Law. It's Charles Boyle.
Right.
I don't know if it's a coincidence.
I only did seven. You know, gas and
Also, the negative pressure.
No, you can't do it. You have to have pressure. You have to have something on the outside.
Oh, okay.
We came to the middle ground of space is not a perfect vacuum. So in actual space, if you got the vacuum strong enough in the can, it would crush because there is some amount of pressure outside. But if you had a perfect vacuum outside, you could not crush it. It would expand out. If you had a perfect vacuum outside and a perfect vacuum inside, then it would just sit there.
Yeah. I was thinking more along the lines like, the vacuum can't be negative pressure, if that makes sense, is what I'm saying.
Yes.
Yeah.
You can't,
So,
because zero pressure is the absence of gas.
yeah,
So to have zero pressure, you have to have negative amount of gas.
that's what I thought was being thought there. So I was,
It's
both make sense, but
it's a matter of, it seems to us that there's a suction. But it's actually not a suction, it's a push. But it's a push by something invisible. So it looks like it's a suction. Okay. So this is the same type of problem. This is Charles' law again. We got the same equation. Which variable are we trying to find? V2, right? So what is V1?
1 or 15.
15 liters. What's T1?
Something
That converted to Kelvin, right? What is T2? That converted to Kelvin, right? Then you have three things. You can plug them in and go. We're not gonna take time to do that. It's algebra. The hard part is picking the stuff.
Thanks. Try to come in quiet.
The hard part is picking the variables out of the question. So that's V1, T1 after you convert it to Kelvin, and T2 after you convert it to Kelvin. Plug it in, do your algebra, and you're done. You get 8.71 meters. So let's keep using our logic brains. What's the relationship, do you think, between volume and the amount of gas? Same direction, opposite direction? Same direction. If you had twice as much gas, it's going to take up twice as much volume. That's probably the most logical of them all, right? So volume is proportional to the number of moles. Here, moles is abbreviated by a lowercase n. Think of it as number of moles, okay? To help you remember your n. This is Avogadro's law. The same guy who brought you your favorite number. Another part of Avogadro's law is this. At something called STP, STP is standard temperature and pressure. So at a given defined temperature and pressure, 1 mole of a gas, any gas, it doesn't matter what gas it is, has a volume of 22.414 liters. Normally this gets shortened to 22.4 liters. This is any gas. It doesn't matter what it is. So STP is 0 Celsius and 1 atmosphere. Okay? I think this is on the cheat sheet. It says standard pressure equals 1 atmosphere equals 760 millimeters of mercury equals 760 torr. So you don't need to remember that. It also says standard temperature is 0 Celsius or 273 Kelvin. So you don't need to memorize the numbers, you just need to know what STP is, what it means. So at 0 degrees Celsius and 1 atmosphere, if you have 1 mole of a gas, it will be 22.4 liters. No exceptions. So here we're going to use that. Okay? So our equation for Avogadro is V1 over N1 equals V2 over N2. Which variable are we trying to find in this problem? Yes. So what is V1? 8.2 liters. What is N1? 0.35 moles. What is V2 is what we're looking for. What is N2? 1.2 moles. So luckily we don't have to convert anything because there's no temperature involved. So we can just go 8.2 divided by 0.35 equals V2 over 1.2. V2 equals 28 liters. 28. We can take all of these together and make one master equation. Okay? The combined gas law. The combined gas law is on the cheat sheet, but their version of the combined gas law does not have the ends in it. So if you want to remember this one, you're welcome to, but they give you the combined gas law without the ends, and they also give you Avogadro's equation. They give you this equation. So in that, if you had a problem involving moles, you could just use this one instead of the combined gas law. Okay? But if you have the master equation, you can do any of the problems. It doesn't matter which variables are involved and which are not. If there's a variable that's not involved, you just erase it. If you have a problem that has pressure, volume, and moles but no temperature, you just take out the t's. If you have a problem that has pressure and volume but no moles or temperature, you just use the top part of the equation. Okay? If something doesn't change, just erase it. So, worst case scenario, there are 8 variables here. The problem will give you 7. You solve for the 8. There's a lot more work to set it up, figuring out what the 7 variables are. But mathematically, it's no more difficult. Solve for the one variable that you're not given. So this means, with that equation, we can change multiple things at once. So before we were changing volume, or we were changing pressure, or we were changing temperature, or number of moles. Now we can change pretty much everything, all at the same time. So here's an example. Let me write this down. P1, B1 over N1, T1, P2, B2 over N2, T2. Which variable are we trying to solve for? V2. We're given a volume to begin with. So what volume would it be with these conditions? So we're looking for V2, which means we have to have everything else. So let's start here. What is my P1?
2.75 atmospheres.
2.75 atmospheres. What is my V1? 1.25 liters. Do I need to worry about my ends? There is no mention of moles, right? So I can just act like moles aren't even in the equation. So now I just need my T1. What's my T1? 80 Celsius turned into Kelvin, which is 353.15 Kelvin. Now we do the other stuff. What's my P2? 5.00 atmospheres. What's my V2 is what I'm trying to solve. What's my T2? 485? 458.15 Kelvin. Yes?
What was the formula for Kelvin again?
Do you take the Celsius, add 273.15. So again, we have one variable we need to solve for. So V2 is what? 0.89 liters. Is that what the slide says? Okay. 891. Yeah, how many? We need 891 liters. So this time, our discount double check is a little more difficult. So, looking at one thing at a time, okay? Did our temperature go up or did our temperature go down? It went up, right? So if temperature went up, would our volume go up or down? Ignoring everything else.
Volume would go up.
Volume would go up. Did our pressure go up or did our pressure go down? If pressure went up, what would you expect your volume to do?
Go down.
Go down. Pressure and volume go in opposite directions. So in this case, they're fighting each other. The temperature is trying to make the volume go up, but the pressure is trying to make it go down. So we don't have a good way of predicting which way it's actually going to go, which one is going to win out. So our discount double check doesn't work here. So that's a summary slide, what we just went over. But if you take it all and put it together, and you do the math, what you get is PV over NT is a constant. Okay? This is going to lead us to the final gas equation, the ideal gas law. Okay? The equations that we talked about already deal with changes. You're starting somewhere and you're changing something. The ideal gas law involves one sample at one point in time. The biggest issue here is these problems is figuring out which equation to use. Look at the question. If something is changing, you need the gas laws that we already dealt with. You can go straight to that combined gas law. If you look at your question and nothing is changing, it's talking about one point in time, this is the only equation you need. This is the only equation you can use if nothing is changing. So this is PV, pressure volume, equals number of moles times R times T. R is a constant. It will always be the same number. Doing experiments, people figured out what that is. 0.0826, 0.08206. Okay? Liter atmospheres per mole Kelvin. Okay? Don't worry about too much about that unit. The value of R is given right here on it's the second thing on the cheat sheet right under Avogadro's number. It's given to you in multiple units. There's 3 numbers depending on what the units are. The one you want is the first one, 0.0821. Most people round this to 0.0821. Okay? So when you do ideal gas law, that means you have to use these units if you're using this value of R. Your volume has to be liters. You cannot use milliliters if your R value has liters. You have to use atmospheres. You can't use torr if your R value has atmospheres. You have to use moles and you have to use Kelvin. In this case, your units are set by your value of R. So let's use it. So take a look at that question and make sure you can see the difference between this type of question where it's one point in time versus the other ones we were doing where things were changing. So what is our ideal gas law? What's the equation?
PV equals nRT.
PV equals nRT. That's going to get drilled into your head after the homework and everything. You're going to remember that for the rest of your life probably. PV equals nRT. So which of these variables are we trying to find? Which one is not given to us?
But you don't-
Right. It says what mass. Mass isn't in here. But if we find moles, we can get the mass from that. So are we given P?
Yeah.
What is our pressure? 700 torr, but we have to get it to atmospheres. So there are 760 torrs in an atmosphere. So it's 700 divided by 760. 0.920 atmospheres. What's my volume? 6.0 liters. Luckily that one's in the right unit already. Equals N, which is we're trying to find. What is R? 0.0821. I'm not even going to bother putting the unit on it. PV equals nRT. What's my T? In Kelvin, that was 298.15 Kelvin. Solve for N. So you solve for N, hopefully you'll get 0.0226 moles. How can we get to gram? The question asked us for mass. Do moles to gram. So we got 0.226 moles of oxygen gas. Divide what's the mass, or 1 mole of O2 equals how many grams?
7.2. Well,
What's the molar mass of oxygen gas?
15.45,
32.
Oh,
Yeah, it's O2. Don't, if you're working with that's a gas, it's diatomic. Don't forget that it's diatomic. That's going to change your answer by a factor of 2. If you put 16 here versus 32. So it's oxygen gas, which is diatomic. You have 32. It's 32 times 0.226. Three. 7.23 grams of oxygen.
I thought we were done.
Hmm?
I thought we were done with that. The moles to the grams.
That you're not done.
wouldn't it be 1 sig fig because of the torus?
Nice. Yes, it would be. There's no point there. So that's 1 sig fig.
Look at you go.
I need my stamp and stamp my work because I got the sig figs wrong. So 7 grams of oxygen. Where did they get 2? Oh, from the 6.0. The book missed the 700 too. I'm not the only one. It's a plight we all face. Sig figs. Here's another one. Which variable are we which variable are we looking for? We're looking for moles. Hopefully you got it from the question, not the title.
I didn't even read it.
Yeah.
I didn't
Okay.
read the title.
How many moles of oxygen? So we're looking for N, so we have to have everything else. What's my pressure? 723 torr, which is how many atmospheres? 0.951 torr. What's my volume? 2.025 liters. N is what we're looking for. What is R? 0.0821. And what is T? 302.35. Solve for N. Point 0.0776 moles. What's the difference? I remember there is something different.
You're solving for
Everything's different, isn't it? All the numbers are different. So this time we've got, what's our pressure? 755 divided by 760?
Yeah. But it's 0.993.
0.993. Oh, this is, sorry. This was atmospheres. Atmospheres, 1.85. Oh, we had to write this one there. So N 0.0821, and the temperature is 291.25.
Yeah.
N equals 0.0769 moles.
Yeah.
And it's oxygen, so we can take that 1 mole. Oxygen is 32 grams of oxygen equals is that even up there somewhere?
Yeah, it's the next one.
Oh.
I feel like when you do the work on a board, it's much easier to understand that.
I'm looking, they try to put everything there, but it just turns into so much.
Well, you do a different thing.
Yeah. No, which is why I keep these here. If you prefer their way, they both get the same number. So you do whichever way you prefer. Okay. More brain busters. We have 2 balloons. This is an optical illusion. They're both the same size. To me, the orange one looks bigger, but they're actually the same size. Which balloon has the greatest number of gas molecules?
Carbon dioxide.
CO2.
What if I told you you're all wrong?
Are they equal?
They're equal. Why are they equal?
It's all the same.
The volume is the same. And the volume is determined by the number of moles. Remember, an ideal gas at STP is 22.4 liters. It doesn't matter what type of gas you have, if all the conditions are the same and you have the same volume, you have the same number of moles. Which balloon has the greatest number of moles? Equal. If you have the same number of molecules, you have the same number of moles. Which has the greatest mass? Why CO2?
It has a bigger molecular mass.
Right. You you have the same number of molecules, but each of those molecules weighs more in the CO2 versus the O2, right? Which one has the greatest density? Why CO2?
I say volume, higher mass.
Right. What's the equation for density?
DOV.
D equals mass over volume. Volume is the same for both of them. So whichever one has the larger mass has the larger density. And we said CO2 has the larger mass. Here, the yellow one really is smaller. Which one has the larger number of molecules?
The bigger one.
The bigger one. CO2 has more molecules. Which one has more moles?
The bigger one.
CO2. Which one has more mass?
The bigger one.
Still CO2.
Right, still CO2. If the CO2 one was smaller than the oxygen one, then it's a toss-up. But the heavier one is also the bigger one, so it certainly has more mass. What about the density? How do you know? Density doesn't change with proportion. So the density here is the same as the density here. So here we said CO2 was more dense, so it's still more dense here.
Well, if you said they were the same, if you said they were the same and then you decrease the volume, then O2 would be more dense.
We decrease the volume by taking gas out. So we decrease the mass and the volume at the same ratio. So density stays the same. One final equation. I think I said that last time, didn't I?
Yeah,
I honestly don't think there's one after this one.
I hope not.
This is Dalton's law of partial pressures. Okay? Yes. This one is on the cheat sheet. What this tells you is that if you have a mixture of gases, each gas has its own pressure. They act completely independent of each other. But the total pressure inside your container is just the pressure of each of them added together. So the total pressure is the pressure of A plus the pressure of B plus the pressure of C. So in this container we have nitrogen gas and oxygen gas. So you can use the equations that we did to figure out the pressure of the nitrogen and figure out the pressure of the oxygen, add them together, and you'll get the total pressure. Okay? The type of question that you're most likely to see here is to say, if you have a container that has a partial pressure, the term is partial pressure if you're just talking about one type of molecule in a container. The partial pressure of nitrogen is 1 atmosphere. The partial pressure of oxygen is 2 atmospheres. What's your total pressure? 3 atmospheres. Add them together.
And we took my new.
Okay, I think this is the last idea.
No, there's 7
Well, this is the last idea. Yes. And there's no numbers involved, it's all words. So, what we've been talking about is, said it was based on this ideal gas. Okay? And the ideal gas behaves based on this kinetic molecular theory. What this kinetic molecular theory is going to say is how we've been visualizing the gases all along. Okay? It's just taking what we've been saying and putting it into an official format. There are 4 postulates of kinetic molecular theory. Big word, not my word. Okay? Use this. first postulate is that our gases are composed of small particles that are a long ways from each other. Which means that when we have a container of gas, the vast majority of what we have is empty space. Because we have molecules, or atoms, that are very small in themselves, and they're a long ways away from each other. So there's all that empty space between them. So that is why we say that the volume of our gas is completely independent of what type of molecule we have. The CO2 molecule is larger than an O2 molecule. But the volume actually taken up by the molecule in our sample of gas is insignificantly small. Because the vast majority of what we have is actually empty space. So it doesn't matter. It doesn't make a difference in the real world. This tells us why gases have such low density. We have a lot of volume in very little mass. Also tells us why we can compress gases. Have you ever put water in a syringe and tried to push it? It doesn't work very well, right? But if you've got gas in there, you can push it for a ways before it stops you. Second postulate is that each of the molecules behaves completely independent of each other. This says that there are no attractions or repulsions between them. It's like they don't even know they exist, which means that they fly in straight lines. If you have molecules flying in straight lines, they behave independent of each other. But if you have a molecule here and they don't follow this postulate, there's attraction between them, you're going to get curved flight. And then everything goes out the window. So kinetic molecular theory says each of the molecules behaves completely independent of each other. The only time they interact is when they hit each other. In those cases, they do interact, but they just bounce off each other. They don't stick together. They don't lose energy. They just hit each other and move on like a pool ball. Third postulate is that, like I said, they move in a straight line. They move very fast, and they move in that straight line until they hit something, whether it be another gas molecule or the side of the container. They just keep going until they hit something, and they bounce, and they go until they hit something. We say the collisions are elastic, perfectly elastic, meaning the energy is not lost. Think of a pool ball. For the most part, when they hit, they don't lose energy. But if you have two cars hit each other, they crumple and they just kind of stop. That's an inelastic collision. And the fourth one is what we've been talking about. The pressure is just from the molecules hitting the inside of the container. We've already talked about that a number of times. So, the smaller your container, the more often the things inside hit the wall, the higher the pressure. Right? This also says that pressure should be proportional to the number of molecules. If you double the number of molecules in your container, you're going to have double the number of molecules hitting the wall. So you get double the pressure. Might want to go back and change the other slide. And I said there was 4. It doesn't really make a difference. But apparently there are 5. Okay. And the average kinetic energy is based on temperature. Nothing else. Increase the temperature, average kinetic energy goes up. Which tells us, don't worry about that, but this is why increasing temperature can increases speed. Kinetic energy is measured by temperature, right? This is the equation for kinetic energy. If you increase kinetic energy, you're going to increase your velocity v. So if they're hotter, they have higher kinetic energy, they're moving faster, they hit the walls more often, higher pressure. If you have two gases and they have the same temperature, that means they have the same kinetic energy. That does not mean that they have the same velocity, because this equation takes into account mass. So kinetic energy is a product of mass and the velocity squared. So if you have two molecules and they're the same temperature, so they have the same kinetic energy, which one is going to be moving faster? The heavy molecule or the light molecule? The lighter one. Mass and volume are going to go in opposite directions. The lighter one has to move faster to make up for the lack of mass. So which one of these three has the greatest average kinetic energy at the same temperature? Greatest average kinetic energy, not velocity, kinetic energy.
No.
They're the same. Temperature is a measure of kinetic energy. If they have the same temperature, they have the same kinetic energy. Which has the greatest average velocity? H2. It's lighter, so it has to move faster to have the same kinetic energy. There are problems with our ideal gases. Hint, okay? Important slide. Okay? Seriously, important slide. There are problems with our ideal gas laws. Okay? Our actual gases are not perfectly ideal. The collisions between them aren't completely elastic. When they hit each other, they lose a little bit of energy. And there are attractions between molecules, particularly when you have a high pressure or a low temperature. Circle this slide. Come back to that slide. Okay? So we went over the homework in class on Thursday. There was the one question we didn't do, correct? Which one was it? 6?
did
Stoichiometry
do
problem.
two.
I think it was 6.
It was 6.
It was a stoichiometry problem, right? So does everybody want to come up and do number 6 on the board? Anyway. Yes, thank you.